Welcome back to our second problem-solving video. I'm Perry, and today I'm joined by James as we go over problems 5 and 6 from the 2024 Euclid contest, hosted by the University of Waterloo. These problems are starting to get a bit more challenging, but we'll explain them clearly for you. Here's James with problem 5.
You're given a diagram in which ABCD is divided into four smaller rectangles by the lines PQ and RS, which intersect at X. The areas of these smaller rectangles are in some order 2, 6, 3, and A. So, what are the three possible values of A? For this one, basically, you know that for these rectangles, like for example, the area ratio between rectangle APSX over, like, for example, PXDR is equal to SXQB. And XRCQ. And this is because these rectangles, for example, APSX right over here and PXDR, they have the same height, but their base, which ultimately determines their area ratio, is different. So the area ratio between APSX and PXDR is the same ratio as SX and XR. And since the same can be said for the lower rectangles, which are SXQB and XRCQ, then their area ratios are equal because they're both equal to SX over XR. So we're given three areas of some rectangles, and we just want to find what the area of the last rectangle can be. So let's try a few things. Let's say, well, there's only going to be 4 possibilities because, for example, it can be only 3 actually, if you do all the casework. So here's 2, here's 6, and then if this area is 3, then by this condition, APSX over PXDR is 1 over 3, right? Because 2 over is equal to 2 over 6, and then XQB divided by XRCQ must also be 1 over 3. However, you have that XQB is equal to 3. So that means that XRCQ must equal to 9. So one value of A is equal to 9 then. Now, what if we swap the 6 and 3 here? What if we had make sure erase this. Let's say 3 and 6. You notice that APSX over PXDR is 2 over 3, right? And that's equal to SXQB divided by XRCQ. There it is. And then since SXQB you have is equal to 6, then since this ratio is equal to 6, it's equal to 2 over 3, then XRCQ must equal to 9. So you get that another possible value of A is 9. So this gives you the same answer as earlier though, so that's why we don't need to consider this. And note that in general, if you flip these two values between PDRX and SXQB, the overall value of the overall area of the last rectangle will still be the same. Because if you just apply the same ratios twice, it doesn't matter which order you apply them in. So yeah. So for future values, we don't need to consider like whether or not we flip these two values and get a different answer. So that's one possibility. Now, what if we had like 2, 3, but the 6 was over here? Well, then you have that APSX over PXDR is equal to 2 over 3, and that SXQB, which you don't know, divided by 6, because the area of XRCQ is 6, is equal to 2 over 3. So that means that SXQB is equal to 4. So we have another possible value of the remaining rectangle is 4. And note that this is kind of like this earlier case, right? If we flip 2 and 6 here, like this, the ratios between 3 and 6 and 3 and 2, they're the same ratios as earlier, but we're just applying them in a different order. So we'll still get a final answer of 4 here. So we don't need to consider flipping the two diagonals. Now then, let's consider what if we had 6 in the corner then? Because what we have shown is that it doesn't matter which like order the numbers are in the two diagonals. So the only number that matters and will affect the final area of the last rectangle is the rectangle in the corner between the other two numbers that we know. So if 6 was in the corner, for example, we have like 6, 2, 3. That's one possibility. And as we've shown earlier, this is the same thing. Well, it will give us the same result as if it was 6, 2, 3. Or perhaps we move the 6 over here, same thing. Or if we move the 6 over here to a different corner, it's the same thing. So as long as the number in the corner is the same, like in the corner between the two other numbers that we know is the same, then the area of the final rectangle will be the same. So we don't have to consider like which corner the number between the other two numbers is in, or what like the order between the two like non-corner numbers are. So let's just finish the question by considering if 6 was between the other two numbers we know in this corner. So you have 6, 2, 3 here, and since the ratio between APSX and PXDR is 3, and the ratio between SXQB and XRCQ is also 3, then that means that XRCQ is 3 divided by 3, so it's 1. So the final value of A that you have is equal to 1 then. Basically, as a recap, you get a different value for the remaining area, like the unknown area of the last rectangle, as long as the number in the middle between the other two numbers we know is different. And since we only have 3 different numbers that could be in the middle, being 2, 3, and 6, we'll get 3 values of A. So the answer to this question is equal to 1, 4, and 9. Let's move on to question 5b then. You have a parabola with equation x squared minus 4tx plus 5t squared minus 6t equals y, of course. And that this has 2 distinct x-intercepts. Find the value of t for which the distance between these 2 x-intercepts are as large as possible. So I think the most straightforward way to solve for the difference between x-intercepts is to first just apply the Pythagorean theorem. The quadratic formula. Getting some formulas mixed up here. And yeah, so if you want to find the x-intercepts, so you set y equals 0. So it should be 0 equals, oops, okay. So applying the quadratic formula, you have 4t is a coefficient of x here, so that's b. X equals 4t, and then plus or minus square root of 4t squared, which is right like this. Well, I guess negative 4t squared technically. And then minus 4ac, which is equal to 4. And a is 1, so we don't have to consider it. And c is 5t squared minus 6t. So you divide by 2a, and since a is 1, you just divide by 2. Now, you can try to simplify this, but we don't care exactly what the x-intercepts are. We just want the difference. We just want the distance between the x-intercepts, and that lies in this part of the expression here. So the distance here is just equal to the 2 times the square root expression. Let's just say distance because one side is plus, one side is minus, then the distance between the x-intercepts is 2 square roots negative 4t squared minus 4 times 5t squared minus 6t. So, of course, we still have to divide by 2 because that's still the denominator. And since the 2 just cancel out, like so, you're left with just the square root expression in the original quadratic formula being our distance. So this is what we want to minimize. Okay. So how do we, this is what we want to maximize. Yeah, as in the problem statement, you want to make the distance between these x-intercepts as large as possible. So if we want to maximize an expression inside a square root that has a positive coefficient of 1, then we want to maximize the expression inside square roots. So basically we can just completely remove the square root part, because if we maximize the expression inside the square root, we also maximize the square root of that expression. And if you just quickly look inside the expression, like inside the square roots, you'll see that it's actually just a quadratic in t. So if you do the simplification or expansion that we didn't do earlier, 16t squared minus 20t squared plus 24t you can combine like terms. So that's 16 minus 20, that's negative 4. So you have negative 4t squared plus plus 24t. So if you want to maximize this expression and find the value of t that gives you the maximum value. And the most common way of doing this is just by completing the square, because when you complete the square, then you have an expression that could be very easily minimized. And yeah, so you complete the square here, t squared minus 6t and if you complete the square here, you get negative 4 times t squared minus 6t plus 9, because that would give you t minus 3 squared. But since you added 9 inside this expression, you essentially subtracted 36 in the overall expression, because you also multiply it by negative 4. So since you subtracted an extra 36, you want to add 36 back. And finally, we know that t squared minus 6t plus 9 is equal to t minus 3 squared. And then you have plus 36 at the end. So what do we have here? We have a negative coefficient and a perfect square here. Well, not perfect square, but like some expression squared here, and then a constant term here. So that's what you're supposed to get after completing a square for a quadratic equation with a negative leading coefficient. And we want to maximize the expression. So we note that this expression squared, just by the trivial inequality, is guaranteed to be greater than or equal to 0. And since the coefficient behind this expression is negative, right, as you can see the negative sign here, then since we want to make this expression as like great as possible, and since this expression is guaranteed to be negative because this is non-negative and this is negative, then the maximum possible value for this part of the expression is when this expression is equal to 0. Because if it's greater than 0, then this expression is more negative. So that would make the overall like result not maximized, basically. So we can maximize this by setting this expression equal to 0. So if we have t minus 3 squared is equal to 0, then we can easily see that t must equal 3, because that is the only way to make a perfect square 0 is by making the expression that you're trying to square 0. So get t equals 3 here. And that's it. So basically, as a recap, when you see that the question wants you to maximize the distance between x-intercepts, first you can find an expression for the distance between the x-intercepts, and you can do that through the quadratic formula. Then you find the distance, since you note that one side is plus, other root is minus, so the overall difference will be 2 times the expression over here. And of course you still have to divide by the denominator, so you have the distance as an expression of t. And since you want to maximize some expression that is like square rooted, you want to maximize the expression inside the square root, because if you maximize that, then you also maximize the expression after taking the square roots. After simplification, you get a quadratic in t. You can apply well-known methods like completing the square. And finally, determine the value of t that maximizes the expression by the expression you get from completing the square. So t equals 3 is a solution for question 5b here. So yeah, this question is just applying like the methods that are commonly used in math contests like these, and even in high school math. So yeah, without further ado, let's see if Harry wants to do question 6.
Okay, so this is going to be the last question that we're going to do today. Let me insert the questions. Alright. So, for question 6a, the question reads, there are m integers between 10,000 and 100,000 that are multiples of 21 and whose units digit is 1. And it wants us to find how many of these numbers there are. So, what we can do is, let's first figure out what it means for a number to be a multiple of 21 and also have units digit 1. So there's actually two ways to do this. There's one way using slightly more advanced methods with modular arithmetic, and there's another way that just uses kind of pattern finding to figure out kind of what the characterization of multiples of 21 with units digit 1 is. Let's do the first method, where we're just going to look at some multiples of 21. So the first few multiples of 21 are 21, 42, 63, 84, 105, 126, 147, 168, 189, 210, 231, ... And what we want to look at is the units digit of each one of these numbers. And what do we notice? We notice that they form a loop, and they increase by 1 each time. So units digit is actually 1, 2, 3, 4, 5, 6, blah, 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 until eventually we get to 1 again. So we have that for some positive integer k, 21k will end in k as the units digit. This is actually only true for k between 1 and 9. So then, to correct that, we actually have that 21k will end in the same digit as k. So if you know some modular arithmetic, you can show this a little bit quicker. Modulo 10, we have that 21k is congruent to 20 plus 1 times k, which is just congruent to k modulo 10, which gives the same result as above. So now we know what we want to count. We want to count multiples of 21 that end in 1, so 21k for k ending in 1 between 10,000 and 100,000. So now let's figure out what the bounds that we have are. We want the number to be between 10,000 and 100,000. So we have 10,000 is less than or equal to 21k is less than or equal to 100,000. We can divide by 21 on the left and the right to get that 10,000 over 21 is less than or equal to k is less than or equal to 100,000 over 21. You're going to plug these numbers into your calculator. The first one is around 476.2, less than or equal to k, and less than or equal to around 4,761.9. Since k is an integer, we know that k can't be 476 or less. Therefore, we have like 477 less than or equal to k is less than or equal to 4,761. Now we only care about the k that end in 1. So these numbers, the smallest one that works is 481, and then after that we have 491, all the way up to 4,761. So now the final step is just to count how many of these numbers are there. And so there's an easy way to do this, is to note that if you just delete the ones at the end of every number, like the number of them will stay the same, so then it turns out you're just counting 48, 49, up to 476. And then if you subtract 47 from each one of these numbers, it's the same as counting 1, 2, up to 429. And clearly there are 429 numbers in this list because that's how counting works. So there we have it. The answer is m equals 429. That was question 6a. So now let's move on to 6b. I'm going to do that on the side over here. So let's read the question first. There are n students at some school where n is between 500 and 600, and 2/5 of them are in the physics club, 1/4 of them are in the math club, and then we have some relations between students that are in one club but not the other, and etc. So a very good way to model this information is with a Venn diagram. So let's draw a Venn diagram. We're going to let this one be P, this one be M for physics and math, and then, so what do we know? We can let the number of students in physics but not math, so that's kind of this area over here, that's A. We can let math but not physics, so that's this area over here, that's B. And then we can let the ones in both be C and the ones in neither be D. So now, what are the equations that we know? First, we know that there's a total of n students. So A plus B plus C plus D is equal to n. Next, we know that 2/5 of them are in the physics club. All the people in the physics club are represented by A plus C, so you have that A plus C is equal to 2 over 5n. Similarly, we have 1/4 in the math club, so B plus C to 1/4 n. Since A, B, C, and D are all not necessarily positive, but they're all integers, this means that both of these expressions have to be integers. Therefore, we have that n is a multiple of 4 and 5. This means that n is a multiple of 20. So that's just something to note first. Finally, the last condition is that in the physics club, there are 2 times as many students who are not in the math club as there are students who are in the math club. What does this mean? This means that A is equal to 2C. That's what the given condition says. If we plug this in to this equation over here, this gives that 2C plus C is equal to 2 over 5n. So 3C is equal to 2 over 5n. So C is equal to 2 over 15n. Since C, again, is an integer, this means that 15 divides n as well. If we take both of these two conditions and combine them over here. We note that if a number is divisible by two other numbers, then it's also divisible by their lowest common multiple. Therefore, we have that LCM of 20 and 15, which is equal to 60, divides n. Now, we are given that 500 is less than n is less than 600. Since n is a multiple of 60, we see that in this range, you have 480, which is too small, 540, which works, and 600, which is too small because this is strict inequality rather than non-strict inequality. Therefore, the only possible value of n is 540. Now, this is not what the question is asking for. It's asking for the number of students who are not in either club. So we still need to actually solve these equations to figure out what D is. So now that we know what n is, we can rewrite our two equations above. We have that a plus c is equal to 2 over 5 times 540. This is equal to 216. Moreover, we know that a equals 2c. So then this gives that c equals 216 over 3, 72. And a is equal to 216 minus 72, which is equal to 144. So now we know what a and c are. Now, from the second equation from above, we have that b plus c is equal to 1/4 of 540. This is equal to 135. Therefore, b is equal to 135 minus c, which is equal to 63. Finally, we know that a plus b plus c plus d is equal to n. So d is equal to n minus a minus b minus c, which is 540 minus 72 minus 144 minus 63, which is equal to 261. And that is our final answer.
We hope you've enjoyed this video and learned some new strategies and ideas. Make sure to subscribe to our channel so you don't miss out on any of our future videos, and we'll see you guys soon.